Hello, everybody. Thank you for coming to this presentation. I am Björn Fahller. I live in Stockholm. I work for a company named NetInsight. We do networky stuff, make network equipment like these, for example, or these. I have no idea how many computers are on these, because on every plug-in board there are at least 2 CPUs and at least 1 FPGA. So quite a lot. And then, of course, we connect these in large networks. Media companies, media broadcasters love these. And we make everything from designing the mechanics, low-level software, the electronics, low-level software, FPGA programming, network stack services, network management systems, everything. So full stack, really full stack. But let's not talk about that. Let's talk about jigsaw puzzles. Did you know that manufacturers of jigsaw puzzles have standard cutout patterns that they use several times over for different jigsaw puzzles? So that if you buy 2 different jigsaw puzzles from the same manufacturer that has the same number of pieces and the same geometry, the pieces almost certainly fit together. This artist, Tim Klein, who made this, he certainly knows it. So if you go to this website, puzzlemontage.crevada.com, you will see several. And I'm going to shamelessly use a few in this presentation, because this behavior reminds me very much of the C++ type system. You see, if you haven't thought about it, C++ has a small set of standard jigsaw puzzle piece shapes that fit together the way you want to, or in a number of other ways also. But unlike a jigsaw puzzle that you buy, C++ allows you to create your own shapes, and you can make them as generic or as specific as you want them to. And you, as programmers, you use this. You create types that make up the structure of the program. So you have all the monsters here and all the network requests waiting for a response and all the unpaid bills and all the customers, they are there. They are different types. You have these in your program. But in my experience, programmers rarely use the types for the information passed between these pieces. And I intend to quite subversively tweak your brains a little bit here, so that when you go back to work after this conference, you will start rewriting your software. Because, yeah, you rarely do this, but C++ allows it. So I intend to show a number of examples of code that has various kinds of problems, and I promise you, you will recognize almost all of these in your code. And I will show ways to improve matters. The things I show you are examples. There are other ways of solving the same problems. The important bit is to think about, how can I use a type system to make my program better? So let's dive into one of my favorite examples, the wrong argument. So we have here some software that reacts to some kind of user input, queries a database probably based on that input. But we have a problem here. So we sanitize the input because we don't trust users, they write weird things. And we log this sanitized output because it can be good to have for diagnostic purposes. But we have a mistake. The query is made with the unsanitized input. That is probably not good. But the thing is, you don't want your program to become a topic of an XKCD comic. You don't. But the thing is, the person who wrote this knew this. That's why sanitized input is there. It's just a silly mistake that was made, that they happened to make the query with the unsanitized input. So what can we do? Well, one thing we can do is we can change the signatures of sanitized input and query user data so that they take a sanitized string instead. And a sanitized string must not be possible to just accidentally get from a standard string. It must be something you have to actually call sanitized input, or make some effort at least to get a sanitized string. So how can we create something like that? So this extremely advanced piece of code. I should have said this in the beginning. I know that I have a history of presenting some fairly advanced pieces of code. This is not that talk. I fully expect a very junior programmer to be able to follow everything. But at the same time, I think most senior programmers will learn new ways to apply the knowledge that they already have. So here's this very advanced piece of code that actually fulfills our needs. This cannot be, if you have a string, you will not accidentally get a sanitized string. You have to make an effort. You have to explicitly create it. And likewise, you will not accidentally get a std string out of a sanitized string. You have to explicitly say that you want to get the data member, that dot value. So it's not perfect, but it's not bad. So when we do this, and we have this bug, we get this compilation error saying that reference of type const sanitized string ref cannot be created from a std string with the normal compiler error message encryption. But this is vastly preferable to an angry customer call and a debugging session, even if it's annoying to get the compilation error. We can do a little bit better, though. How about creating a real sanitized string type that does something a little bit more? So this thing in the green box here is a conversion operator, if you have not seen those before. The way they work is that, in this case, I have a function work that takes an int, and we have a class C, and in the function at the bottom, we have something that calls work with an instance of C. And what happens here is that the compiler sees that I'm supposed to call work with a C, but I don't see work takes an int. C is not an int. But it sees this conversion operator int const. And this is what is called a conversion operator. You almost always want these to be const. You don't want your conversion operator to change your object or to leak its internals normally. To be a little bit more safe, you can mark it explicit. Now it doesn't just happen to become an int. You have to have this static cast at the bottom to say, no, I want this int. Don't just accidentally become an int. So we have this explicit operator const string ref. We have the string is private, so you cannot accidentally modify it. And we also have a constructor, again, explicit. And also, if things are too weird to be sanitized, it throws. Which means that it's very difficult to get a sanitized string that does not have that doesn't have a sanitized string that is possible to use. Because if it's too bad, it will throw, then you don't have an instance. If it doesn't throw, you have to explicitly ask to get the string representation, and the API uses the sanitized string. So we can write the code like this. We create a sanitized string from the input. This will either work and be safe or throw an exception. We can log the sanitized input, and we can make the query with the sanitized input. And if you accidentally, again, use the unsanitized input in the query, you will get a compilation error. And in my opinion, this is very clean code. It's easy to read, and it's very correct and very difficult actually to get wrong. So to summarize, even a very simple struct just completely eliminates a whole class of runtime errors. You get a compilation error instead. And private data and throwing constructor makes the right thing easy and the wrong thing hard, which is exactly what we want. And almost always use explicit for constructors and conversion operators. Almost always. There are exceptions, but they are rare. If you have questions, just wave at any time. Don't wait to the end. Yes?
Should you mark constructors which take multiple arguments as explicit?
Should you mark constructors that take multiple arguments as explicit? Maybe. If you don't mark them as explicit, you can, for example, if you have a function that takes a type, you can just, instead of writing the type, you can just write empty curly braces and the values used to initialize it if it's not marked explicit. If it is marked explicit, you have to write the name of the type. So, a resounding maybe. Other questions? Right, let's go on to the next one. A load of bool. This piece is called the Tyrannosaurus Rex, which I think is very apt. We have all seen functions like this. We have a print, it takes a string view and a load of bools. Should we truncate if the string is too long? Should we pad if it's not long enough? Should we add a line feed to the end? And I mean, the function signature looks all right. This makes sense. I hate that line. It's absolutely horrible when you see a function call and it's just false, false, true. Like, what is this? It's not possible to read it and understand what is the intention. It does not give information. A technique that is used sometimes is that you create variables that says line feed equals true, and then you call it with line feed. But since they are all bools, if you accidentally reorder them, it will compile fine. It will look fine, but it doesn't make sense. So what can we do? Well, enum class is great. By doing this, and I really mean enum class, don't use a C enum, they are just glorified ints. Enum class, in this case, it creates 3 unique distinct types called truncate, pad, and line feed. And all of them have members off and on. So you can write the code like this. Print foo, truncate off, pad off, line feed on. This is clear. It's a bit verbose, I admit, but it is clear. Actually, I think this is a kind of verbosity that is good because it adds information, it adds clarity. And since they are distinct types, if you accidentally rearrange these truncate off and pad off, for example, you will get a compilation error because they are not interchangeable types. Although I do agree that there is a problem in the function signature. I haven't actually seen a good naming convention that makes this not look bad, but I'm prepared to pay that price. It's not the end of the world. So on bools in function parameter lists, you almost never want bool parameters, and you especially almost never want several bools. In fact, I cannot remember a single case where I would want that. An enum clause adds the good kind of verbosity that enhances readability. Your code shows intent instead of just naked numbers, or well, true, false in this case. Beware the were rabbit. So we have the same code. It's not great, but we all have this kind of things in our code base, don't we? And it's been working for quite some time. But somebody realizes that, hey, this line feed thing it's almost always line feed. So why not default it to make it a little bit easier? So someone makes this change. It's fine. It's working. It goes on in use for years. But one day someone realizes that this implicit field size that we have, that is not actually very good. We should always provide a field size for this string. So we add a new parameter there. This compiles. No compiler that I've tried this with warns about it. Because bool is an unsigned integral type, and its value space is strictly within the value space of size t. So this is, in terms of the language rules, this is a perfectly safe conversion. So this calls print with foo, a size of 0, truncate being false, and pad being true, and line feed is true by default. A few colleagues of mine were bitten by, not exactly this line of code, of course, but a similar thing a number of years ago. And this was a fairly large code base, a function that was used in many places and had a default, and the parameter types for that call were interchangeable. And they did exactly this. They added a new thing early in the function signature. And it compiled. They of course made the changes that they saw, but there were hundreds of call sites and they missed a couple. And it took them days to hunt it down. Because unfortunately, the program didn't just crash and burn. Had it done that, it would have been easily caught. But it just sometimes behaved a little bit oddly. So beware the dangerous defaults. But what can we do? The previous solution actually solves this one too. We have, again, truncate, pad, and line feed are distinct types, different types. And this makes the call a compilation error, because we cannot convert implicitly truncate off to a size t. The compiler just says, I have no idea what to do here. You have to fix your program. This is but one example of how you do it. And another example would be to also make the field size a type of its own that isn't convertible from bool. And probably you should do both. But the important thing is that you really don't want arguments of convertible types next to each other in the call chain, especially when you have defaults at the end. Because that just opens the gate for new problems. And this is a different type of problem compared to the ones I showed earlier. The earlier ones were problematic directly when you wrote the code. This works fine, but it is dangerous when the code evolves. So it's working fine as you have it, but suddenly you make a change and boom, you get a very unexpected side effect. But again, distinct, unique types that are not interchangeable saves the day. So, as I said, default parameters are extremely dangerous over time if the parameter types are interchangeable. If they're not, it's fine. And unique and non-convertible types catch this. You get compilation errors if you make a mistake. How the West was won. if I remember correctly. This one is a beauty. So I work with networking, and the networking APIs often look like this, and you get callbacks or whatever. You handle network packet data as a contiguous piece of bytes, and very often you just get a pointer to the beginning and the length. The POSIX APIs, for example, are all of them are like this. So in this case, we have some function that receives a packet, we parse the header, and then we want to copy the payload of the packet that comes after the header. So copy payload, we add the header length to the start so that we don't copy the actual header again. But we should have reduced the length. So now we have a read past the end. We have a buffer overflow situation. This is how your programs make the news. But what is actually the underlying problem here? So, in my opinion, the problem is that we have two parameters that together describe one thing. The one thing is this contiguous block of memory that can be inspected. That is the thing. So let's write a type that represents that. So I can write a very simple buffer view where I have begin and length the same as before, so it's easy to initialize. I use them as const so that we cannot accidentally modify this into something that doesn't make sense, that is wrong. And then I can ask for a prefix where I say, give me the first len bytes. And we create a new buffer view with those. Now there's a decision to be made. What should you do if the length asked for is longer than what actually remains in the buffer? And I cannot say what is the right thing to do. I choose to truncate. Maybe the right thing is to abort. Maybe the right thing is to throw an exception. It's probably not the right thing to ignore it. But these are these are engineering trade-offs that you have to make. But just make a decision and document for those who use this what the behavior is. And instead of modifying this buffer view, we create a new view into the same block of data. So this is safe. It is difficult to accidentally get this wrong. So now the code becomes this. Receive packet takes a buffer view. We parse a packet to get the header, parse the header of the packet to get the header as a sub view, if you like. And then we copy the payload as the packet, the suffix of the packet after the header length. I think this is good code because this, instead of trying to read the arithmetics that goes on, the code actually says what you want to do. It expresses intent, which means that the risk of error is reduced. I mean, you can still, of course, have a bug in the implementation of suffix after or prefix, but I would say it's a reduced risk because you say what you want to achieve. But, of course, we all know that immutable data is problematic. For example, it means that if we have a vector of buffer views and we want to erase one in the middle, that will not compile because if you erase something in the middle, it shifts those towards the end by copy assignment or move assignment. But that won't work when you have const members. So maybe we should do something a little bit more sophisticated. We have our buffer view that has the private members, but now they are mutable. And we need some way to access the underlying data. I choose to have begin and end because that plays nicely with STL algorithms and range 4. And for the love of everything that is sacred, please, 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 please show restraint here. Don't write more than is needed. Write exactly what you need right now, nothing more. It is so easy to be carried away and say, yes, and someone will want a function to calculate a checksum, and someone will want a function to whatever. And that is a maintenance burden. You have to make sure that these are working throughout the changes of the code, and maybe no one will ever use them. So John Carmack of ID software fame said this very good. It's hard for less experienced developers to appreciate how rarely architecture for future requirement or applications turn out net positive. I'm guilty of having done this, but please try to restrain yourself. Write what you know that you need right now, because, I mean, you know it, it's needed, so you write it. And if it turns out that someone actually needed something else, you can go back and change it. It's software, it's soft, you can change it. You're allowed to do that. It's not written by God Almighty, it's written by Robert 2 desks away. Talk to Robert. Yeah. So write small types that are exactly what you need right now. Add stuff if you need to. So the thing with coupled parameters is that when several parameters together describe one thing, try to model that as one type that describes the thing. And from C++ 20, we got studspan that models this start plus length thing. This is great, but you probably don't want to use studspan in your APIs. Sometimes you do if you have very generic functions. But in this case, we are talking about functions that work with network buffers. It doesn't make sense to pass a stud string to that or a stud vector. That is a different thing. And studspan would take those. But by all means, implement your buffer view in terms of studspan. And if you do, this is something that few people know. You probably want to use studspan of const uint8 t. Because the span itself, who watched Victor's talk yesterday about regular types? A handful of people. So you know his takes on span and why it's dangerous. The span itself doesn't own the data, it refers to it. And a const span still refers to the same thing, and if the type it refers to is not const, you can still modify that data through a const span. But if you write a span of const uint8 t, then you will not be able to modify it because it's a const uint8 t that it refers to. I forgot the name of this one, I'm sorry. Too many defaults, yeah. So we have some kind of server socket abstraction for IP, and we want to get which port should we listen to? And they are almost always TCP, so they're hardly ever UDP. So it makes sense that we default it. And which address should we listen to? Well, it's almost always 0.0.0.0, which is listen to all network addresses that this server has. But occasionally you want to be able to change it. And sometimes maybe you actually want to subscribe to a multicast group, but that is rare. So default it to null opt. And should the IO be blocking? Well, probably not. So non-blocking is true. But what if I want all the defaults, but except that I want it actually to be blocking? the rules of the language are such that if you cannot just change one of these. You fill them in from the beginning towards the end. So if you just want to change non-blocking to blocking, you have to add all the parameters, which is noisy and error prone. So what can we do? Well, we can do something quite simple. We create a configuration struct internally here, and we use the initializers of the members to get our defaults. Which means that if you just construct a config, you get all the default values. And then you can modify them to make deviations from the defaults. If you're in C++ 20 or later, you can use the designated initializers to be very clear about what it is you want. So say, no, it's a server socket on port 1666 on localhost instead of on all networks. And in this case, I want the I/O to be blocking. This is nice. It's readable. Before C++20, one way of doing this is just start with default constructing, and then you make the assignments to the deviations from the defaults. It's okay. But omitting .port is not an error. If you have a very recent GCC, it will warn. Clang and MSVC will not warn. And the reason for this is that this is extremely well defined by the language, so exactly what should happen if you don't give a value to port. It will be initialized to 0. So nothing to warn about. It's probably not what you want. So enter the most advanced piece of code you're going to see today. It's advanced because it's a template. So must init of t. It holds t as a value, and I don't know if you know the rules for when the compiler is allowed to make a constructor for you. But when you have added a constructor that takes some type or several, the compiler is not allowed to generate a default constructor for you. So by having this must init that takes a value, you don't have a default constructor. And then we have these conversion operators to get the underlying data. I am violating the recommendation I gave earlier about conversion operators that it should almost always be explicit, but almost, not absolutely always. In this case, I think it is okay, because, for example, with the port, I want this to, for all practical purposes, just be a uint16. I just want to ensure that it's not default initialized, that you must give it a value. So I think it's okay in this case. If you would write this code and ask me to review it, I wouldn't complain, but I also wouldn't complain if you actually did make these conversion operators explicit. And I wouldn't complain if you made the constructor explicit either. It's all right, but I don't think it's necessary in this case. So with this, if we change our struct now to have a must init uint16t for port, it is a compilation error to not give it a value, which saves some head scratching and debugging time. So use this. Feel free to use this example in your code. So creating structs with parameters is especially helpful when many of them have reasonable defaults. Yeah, you can argue about the reasonability in that example, but whatever. And since C++20 with designated initializer syntax, it's extra useful because it makes the call site so clean. You just write curly brace and the dot name equals value, dot name equals value, dot name equals value, and it's very clear what you want to do. I'm going a bit too fast. I'm going to end early. You're not asking questions. Okay, wrong key. This one is interesting. So this is a very contrived example. We have some kind of controller over networking sessions, and it keeps track of both client sessions and server sessions. And we have at the top this server ID and client ID that we use. And we have this closed server that takes a server ID. Wait a minute. That is confusing. That is probably not what was intended. So what can we do about this? Well, to begin with, the root of the problem here is that we use type aliases for client ID and server ID. These, for all practical purposes, these are ints. There is essentially a comment that says this int is called client ID. Compilers don't read comments. They don't care. If you give it a file descriptor, if you give it a random number, it will be perfectly fine. So again, let's revisit enum class, but in a different way. So now I say enum class client ID :int, which means that this client ID is, for all practical purposes, an int, where it's implemented in terms of an int. Its underlying type is int. But note that there are no enumerators. There are no names in there. This creates new unique types. You can use this technique for any integral type. And this was added in C++17. So when you have this mistake, then you get a compilation error and not a debugging session. So that is always nice. The way these work is you can initialize them with a value of the underlying type, like so. And you can assign them and copy them. You get the underlying value by a static cast. Or if you're in C++23 or later, you have access to the underlying function. You can write that yourself if you're not on C++23. It's not particularly difficult to write. And you also get equality comparisons and ordering for free. The compiler does that for you. So an enum class of an integral type with no enumerators is a regular and ordered, strongly ordered type. And therefore it can be used as a key in a map. This is a little bit verbose though. Closed server, server ID, server session, etc. We can actually reduce this now if we want to. So we don't really need to refer to the server or the client in the names of the functions because the types carry the information. So if we want to, we can do overloads like this: closed session with a server ID, a closed session with a client ID. Because you can overload functions on different types. These are distinct types, unlike the type aliases, which are, as I said, they're comments. You cannot overload on a comment. Whether you want to do this or not is a design decision that you probably want to discuss with your team. But now, when they are unique, distinct types, you have the option. Before that, you did not have that option. All right, but what if the keys aren't of integer types then? How do we handle this? Because the enum class only works with integer types. What if I want to use a std string as the underlying type? We cannot have an enum : string. It doesn't work. Well, we can write something like this. I have a server ID, an explicit constructor from a string, explicit conversion operator to get to see its internals. And now I'm on C++20, so I use this magic starship operator to get all the comparison operators, equality and ordering. And I can just default it, then it will be by member. So if you have several members, you will get lexicographical ordering. And that is actually all you have to write if you're in C++20. So that is cool. It's not a lot of work. So you can solve this problem with a few lines of code, even for underlying types that are not integral. So enum class is great for creating new integer types. Spaceship operators is awesome. It's absolutely fantastic. It saves you a lot of work. And avoid the use of aliases in function signatures. Now, type aliases are tremendously useful, but not in that context, not as in function parameters. So, we're at the end now. I said I would end early because you're not asking questions. Types reduces the risk of calling functions with the wrong values. They reduce the risk of reordering. They reduce the risk that dependent values diverge, like in the case of the network packet buffer. Types make it easier to manage defaults, like in the configuration construct where you had the members are given initializer values directly in the declaration, and you can use designated initializer lists to state your deviations from the defaults. Types make your code more expressive. Because, well, I will actually get back to the because soon. The important thing here is actually the last two bullet points. It is rare, at least in my experience, it is rare that you know upfront which types you need. You discover those as the program evolves and your understanding of the problem domain evolves. And when you realize that, wait a minute, this should be a type that is distinct from other types, write that type and incorporate it in the code. And as you do this over and over, the code evolves. You get what I call inverse code rot. You know this idea that your design starts beautiful, you have this great idea, and then reality hits and it just degenerates and becomes worse and worse and worse. But you get the exact opposite. As you learn, you write new types, you incorporate those types in the existing code base, refactor, make new types, refactor. The code becomes easier to read because the code now starts to communicate in terms of the problem domain instead of in terms of the primitives used to solve the problem in the problem domain. So your code now begins to talk in terms that people who are not deeply familiar with the implementation can understand the meaning of. I want to refer you to two other presentations on this topic. They are very different presentations. The first one, Shandor Dargo did at C++ on C last summer, where he looks at the specifics of creating strongly typed containers so that two, say, vectors of int are not interchangeable because they are different things. And he goes through a number of different ways of solving this and talks about their advantages and their disadvantages. So it's highly recommended. If you want to dive into this more about how you design your types, Peter Sommerlad's presentations from CPPCon 2021 is amazing. what classes we design and how. Because Peter's observation is that you only have a handful of categories of types. And these have different rules for how they should behave. And if you have adopted that wisdom and you understand the different categories of types, then when you design your new type, you can think, but this is a handle kind of type, therefore it should behave like this, for example. This makes your types less surprising for your colleagues because they follow a familiar pattern. And it makes it easier to communicate with your colleagues about how a type should be designed. And of course, visit the Tim Klein's webpage for more of these amazing jigsaw puzzle mashups. They are actually for sale, so maybe actually buy one and hang it on your office wall to remind you of using the type system. And with that, I am done. Thank you very much for your kind attention. Maybe now you're not too shy to ask questions.
So I understood your load of bools and wrong key examples. Your solutions to them are effectively defining strong type aliases. And some other languages have a core language facility for defining strong type aliases, for example, new type in Haskell. Do you think it would be a reasonable addition to C++ to have such a syntax?
Yes, I do, but I'm not sure how I would want that to look. Because as I mentioned about Peter Sommerlad's presentation, you have types of different categories. So you may want to limit your types to, this type should allow these operations, this type should allow those operations. And I'm not sure how you would want to model that in the language. But I definitely think that we want some kind of mechanism to be able to do this, yes.
Thanks.
Okay, well, so far we have no questions from the online audience, but I have a question,
right.
And that is this trick with the enum for integral types. Does that mean that all these strong type libraries that I think you and Peter have written are defunct, at least for integral types?
No. They are not, because of the reason for the answer for the other question. So if you look at my library, that is the one I know well. The others I have superficial knowledge about. You restrict your type. My default is a handle kind of type. It's regular. You can give it a value. You can compare it for equality. You can copy it, and that's pretty much it. And if you want to model, say, a file descriptor, that is exactly what you want, nothing more. If you want to be able to do arithmetics on it, that is an addition. You want to say, no, I want this integer to be arithmetic, or I want this integer to be move only. It shouldn't be copyable. Or maybe it should, can I take some example? You get the idea. There are a number of restrictions that you want to make. With the enum class thing, you get a regular ordered type. That is what you get, period.
Okay, thank you.
Anyone else? Right, thank you.